Hey everyone, so before we talk about our next big topic, non-parametric methods, I want to take a few minutes to review where we are and where we're going with the course, kind of like a little bit of a course roadmap. So what have we learned so far? There's a bunch of the topics, on the left there, but I want to kind of put these in the context of the big ideas that we talked about, right? Which are how do we make decisions under uncertainty and how do we understand model assumptions that are being made? And remember, in this course, we're not trying to teach you every single detail of every single algorithm. There's a ton of resources out there for like when you actually need to apply this, in a real world problem. There's a lot of nuance. What we're trying to do is we're trying to give you the tools to say, okay, what is going on here? What are the model assumptions being made? How do I deal with the uncertainty that's present here? And we're also trying to give you the tools to say, well, let's not just think about how do you, apply like the stuff that's like hot and cool today. It's really thinking about how do we give you the tools to understand the fundamentals so you can not just do and learn what's popular today, but also be at the forefront of figuring out what's going to be popular tomorrow, right? And when I say tomorrow, I figuratively mean like the next 5, 10, 15, 20 years. And so it's really about understanding what are the big ideas. We could teach you an entire course on neural nets. Those are like super popular right now. And we're actually going to talk a little bit about neural nets, but we're not going to spend too much time on, how do you build a neural net? Like, what's the computer vision problem? Instead, we're going to talk about the foundation, right? We're going to talk about backpropagation, automatic differentiation, which are kind of like tools that let you do neural nets, but also let you solve a lot of really other interesting problems. And so, with these topics that we've covered, like binary decision making, we spent a lot of time on like, what is this big idea? How do you think about things in this like Bayesian way of like thinking about like false discovery rate, online decision making, right? So not just thinking about the problem from a simple context of like, oh, hypothesis testing, Bonferroni correction, but really, how do you really understand the errors that you're making? With Bayesian inference, we want to really say, how do we encode certain assumptions that we have, right? How do we use a prior? How do we build a graphical model for a problem? For generalized linear models, we talked about, here's this class of models. Here's how we can use it to really like make this, make predictions going beyond just simple linear regression. And we use that to talk about uncertainty, model checking, and so on. We talked about causal inference. How do you determine causality, right, in a randomized controlled trial, but also even in an observational study, right? We talked about concentration inequalities, which are at the foundation of if you're going to do any theoretical probability work in the future. Concentration inequalities are at the foundation of that. And we also talked about bandits, where not only did we apply what we learned with concentration inequalities, we talked about, okay, here's like a really concrete, tangible way that concentration inequalities can help us guarantee that our algorithms are good. We also talked about, here's a framework for thinking about problems, right? Here's a framework for online decision making, right? You have some uncertainty about a number of different choices. These are the arms of your bandit. And how do you sort of account for that uncertainty and see what's going on, right? And throughout, we talked about what are the assumptions that are being made. So now in the next kind of last like big unit of the class, we're going to talk about non-parametric methods. And the word non-parametric has a few different meanings, which we'll get into. But the big idea here is we're going to say, okay, we spend a lot of time on models that make a lot of assumptions, right? In Bayesian inference, you have to specify a prior. You have to specify a likelihood. Now, you have to say, here's how I think the world works. And with non-parametric methods that we're going to talk about, we're going to say, well, what happens if we don't make those assumptions? What do we gain and what do we lose? And so that's kind of where we're going to go for the next week, right? And so the methods that we spent a lot of time on methods that make different assumptions. And we've like really understood, okay, these are the assumptions being made. And here's what I get for making those assumptions, right? For GLMs, I make the assumption that, there's this linear interaction between the features. But then I get the ability to say, oh, this coefficient means exactly this. Or I know that if I have a problem with this structure, I use exactly this link function, right? It's a very clear cut, like here, if this, then do this. With non-parametrics, we're sort of like, things are getting a little fuzzier. And we gain some stuff and we lose some stuff. And we'll talk about where that, what that is and what that means. And then finally, in the last bit of the class, we're going to kind of cover an assortment of topics that help us understand, like what does this look like beyond these sort of like big areas that we've spent a bunch of time on, right? We're going to talk about reinforcement learning. We're going to talk a little bit about game theory. We're going to talk a little bit about differential privacy, right? So we're going to talk about how do we think about this stuff beyond these sort of like major topic areas. And each of those will be like a relatively short, self-contained, fun little bit. But for now, this week, let's talk about non-parametric methods. In this sequence of videos, we're going to talk about non-parametric methods. And it's going to be kind of a whirlwind tour. We're going to cover a lot of ground. So I want to set the stage and give you a sense of like what we're going to cover and why, so that you have kind of a roadmap of where we're going as we like cover a whole bunch of different topics. So we're going to start off by thinking about like, what does even non-parametric even mean? Giving you a sense of like, you know, when are non-parametric methods good? When are they not useful? Because in reality, you will encounter problems, some that, you know, are well solved by non-parametrics, others that are better solved by parametric methods. And we're going to kind of give you a sense of like, you know, when to use one, when to use the other, or at least what the pros and cons are so you can make an informed decision. Then we're going to kind of cover a few really popular, widely used algorithms, decision trees, you know, forests, neural nets. But instead of spending a lot of time on like the nitty gritty of like, here's how the algorithm is implemented and here's how you like, you know, do the best job of fitting it to like get the best accuracy, we're going to step back and focus on what are the big ideas around it. Like, what does ensembling mean? What does bootstrap aggregation mean? What is, you know, automatic differentiation? What is backpropagation? And the reason for that is we want you to be able to, you know, go and take these tools and do data science and, you know, implement a random forest and to solve a problem if you need to. But we also want you to understand the underpinnings, because we want you to be able to not just do data science today, 2 years from now, but also to think about 10 years from now, what are the building blocks that will build the algorithms of the future, right? What are the big ideas that are going to be useful tomorrow, not just like what's, you know, getting you things the best accuracy today. So that's kind of where we'll go today. You know, we'll cover a few different methods, really focusing on the big ideas. And then at the end, we're going to spend a lot of time understanding backpropagation and how it works as well. And then next time, we'll focus on interpretability, explainability, understanding, you know, like some of the trade-offs with non-parametric methods, or sometimes we lose explainability. How do we get that back using some tricks to do interpretability? I want to note that the video sequence for today is a little on the longer side. The stuff for neural nets will not be covered in class until Thursday, so feel free to, you know, space that out. You can watch some of it before Tuesday, some of it later. But we want to have it all there, so it's kind of like one coherent block. And then, you know, the videos for Thursday will be a little on the shorter side overall. Hope you enjoy. Before we can really dive into non-parametric methods, we need to define what the word non-parametric even means. And so there's two different definitions that people will commonly use. In this class, we'll focus on one of them, but it's important to know that they're both out there. And when you see somebody use the word, it's important to know which one they're using. So the two different definitions are, the first is a non-parametric method is one that doesn't make any assumptions about the distribution of the data or the parameters, right? You can imagine, you know, like the Bayesian models that we did, we always had to say, okay, here's my, you know, parameter, here's my likelihood model, here's a distribution of what the data looks like given that. Whereas if you think about something like the hypothesis testing that you learn in a class like Data 8, there's no assumptions about the distribution of the data, right? We sort of have the null hypothesis that's generated purely from the data. We don't actually make any assumptions about the distribution of the data. And so this is kind of the definition that we'll be focusing on in today's class. But it's important to know that there's another definition, which is people say non-parametric to mean methods where the number of parameters is infinite or grows with the number of data points. And what do I mean by that? Well, think about linear regression, right? In linear regression, we have one parameter, which is like one regression coefficient for each input feature. Same goes for like GLMs, where the number of parameters is fixed, right? If I get 10 more data points, then, you know, those 10 data points have like the same features. So I don't actually have to add any new parameters. But there's a bunch of methods where it's like, well, let's not, you know, bother to have a fixed number of parameters. Let's like just let the number of parameters grow. Those methods are kind of beyond the scope of what we'll talk about in this class. But you'll see that kind of approach applied in both the Bayesian and the frequentist context. But for today, we're going to focus on this first definition here. And in particular, this kind of corresponds to the data-centric methods in the Two Cultures paper by Leo Breiman, right? So if you remember, oops, we have remember our setup is always that we have some parameters, theta, that reflect the hidden state of the world, the thing we want to know, right? This is like, what is the average income of people in this neighborhood? What is the true quality of this product on some online marketing site? And what we get is we get some observations X, right? The X is like the data we actually observe. So we don't observe theta, we observe X. It's like we collect the reviews, we collect individual people's income, things like that, and we want to infer what theta is. And there's two ways to go about this. One way is to say, well, I have a model, I have a description for how, if I knew theta, there's a model, or sometimes it's called like a forward model, that tells you, if I know, well, let's maybe use a different color. If I know what theta is, then this is how X comes from. This looks like a likelihood model, something like that. And we have, a lot of inference algorithms we've talked about, right? We talked about Bayesian inference, we talked about GLMs, right? That say, okay, if you know the regression coefficients, then, and your, X's, then here's how your Y's get generated, right? So we have this model that tells us, okay, if you know the state of the world, here's how you get your data. And then we have algorithms that help us reverse that, right? We say, okay, we have this regression algorithm that says, okay, in stats models or PyMC3, here's how we infer the parameters. Or in maximum likelihood, here's how we get the most likely value of the parameter. So these are all kind of the data-centric the model methods that focus on inferring the hidden state using some assumption, some assumed forward model that tells us about the state of the world. Now, the kind of non-parametric methods that we're going to talk about today go the other way around, right? You say, don't bother with the forward model, just figure out what is the best way to figure out what theta is from X, right? So what is the best? So we're just going to build some black box where we don't necessarily have to like fully understand exactly what's going on inside, that gets us from an X to a theta, right? So we just we sort of like build this thing where that we can just plug in X's into it and it'll give us out thetas. We don't have to make any assumptions about what this distribution is. We don't have to like make any sort of, say, oh, I think this is the model or I think that is the model. We just have this black box. And we'll see that this approach has a lot of pros and it has a lot of cons. And which sort of whether you're interested in doing the model-driven or the data-driven really depends on the problem you use and the constraints that you have. And so in the next video, we'll talk about exploring these some of these trade-offs with two models that you've already seen. One kind of like parametric model, which is logistic regression, and one non-parametric method, which is k-nearest neighbor classification. All right, so in this video, we're going to kind of compare and contrast logistic regression and k-nearest neighbor. And remember that logistic regression is an example of a parametric method that we've already learned and are kind of familiar with. K-nearest neighbor classification is an example of a non-parametric method that we've learned and are kind of familiar with. So remember, how does logistic regression work? It says the thing we're trying to predict, y, which is like a 0 or 1 label, or the probability of y, I should say, is the sigmoid function of this linear combination of the x's, right? So the inputs, remember, each of these x1, x2 is a different feature for a single data point. So we take each one, we multiply by some number, beta, beta 1, beta 2, and so on, and then we add them all up, right? So this interaction is linear, right? Remember, this is a generalized linear model example, and we take these, we add them all up, and that gives us our linear part, and then we take that's any value negative infinity to infinity, we run that through the sigmoid function, which turns values from negative infinity to infinity into values between 0 and 1. Another way of interpreting logistic regression is we're predicting the log odds using a linear combination of the x's, right? We say, okay, beta 1 x1 plus beta 2 x2 and so on is equal to log p divided by 1 minus p, right? Remember, this is just, if we kind of do the sigmoid and kind of expand things out, where p is the probability that y equals 1. Also, this should really be a p. And this log odds, like the higher it is, the more likely y is to be 1. The lower it is, the less likely y is to be 1. And so this is another way of saying that, this linear function of the x's should give us the log odds, right? So if this thing on the right-hand side increases by a little bit, then that means that, the thing on the left-hand side increases by that amount. So we can kind of like really, stare at this and look at it and analyze and say, aha, I know exactly what's going on, right? Like it's very predictable. You can clearly see, okay, if I give it data that has, xk values that are like really small, then maybe this coefficient will be really big, something like that. Now, k-nearest neighbor, on the other hand, I can't really write out any equations like this. All I can tell you is a description of how to do it, right? And if you remember, the description of how it works is, first, we start by, to classify a new point, we find the k points in the training set whose x's are the closest to my new point, right? So remember, the way it works is we first give it a training set of like, here's a bunch of x's, here are their corresponding y values. It goes and remembers those. Maybe it optimizes some way of like doing lookups fast, but it remembers those. And now when you want to predict on a new point, we say, okay, for that new point, look at the x for that new point and look at all of the training points, find the k closest ones, right? For those k, look at what their y values were and just take a majority vote. Or if you want to predict a probability, then, just take the average. And the idea there is that if your new point is pretty similar to these other points in terms of their x, then you should have pretty similar values to their y values. So k-nearest neighbor is a non-parametric method because it doesn't make any assumptions at all, right? Logistic regression assumes that, there's this linear function that gives me the log odds, there's this like relationship and, this sort of log odds and sigmoid, and, as this thing on the right-hand side gets really big, then, the sigmoid probability is close to 1. K-nearest neighbor makes no assumptions at all other than the training data should be pretty representative, right? If you give it good training data, then hopefully it should do a good job. If not, not so much. So the only assumption k-nearest neighbors needs is that the training data is representative and the test data is also going to look similar to the training data. All right, so now that we've talked about logistic regression and k-nearest neighbors, let's actually try them out on a data set. So here's a little toy fake data set that I made. So we have two features, x1 and x2, and they're both going to be in the training set from -1 to 1. And y is going to be basically the sine of x1 times x2. And we'll see in a moment what that looks like. We have this useful function draw results, which will draw things for us that we'll keep using. And the training data is going to look something like this. Basically, it's going to be ones where x1 and x2 have the same sign, so like over here and over here, and zeros where they don't, over here and over here. And our training data is going to be from -1 to 1. Our test data is going to be from -3 to 3, just so we can kind of see how the models do as we go a little outside that. Okay, so that's our training data. And now let's try implementing logistic regression. So to do logistic regression, we're just going to use scikit-learn. And we're going to say scikit-learn import logistic regression. We're going to create a model using penalty equals none. And we're going to fit that model to our x and y. Then we're going to use the predict proba method to like predict probabilities, threshold those probabilities at 0.5 to get our predictions y hat, right? And notice that we're predicting on the test set and we're training on the training set. And then this is going to draw the results for first with the color being the probabilities, and then a second plot with the colors being the like binary 0-1 thresholds. And we'll also print out the accuracy. So we can see that the accuracy here is 0.49. And if we look at the predictions, they look like this, which is not very good, right? We're kind of like hoping for that checkerboard pattern, but all we get is something like this. And so our accuracy is like pretty much 50%. This seems really bad. And why is this bad? It's because at the heart of it, logistic regression is a linear model, right? It assumes that there's some linear function of x1 and x2 that we can use as the decision boundary, right? That there's this sort of like, this probability looks like a linear function in some way, shape, or form in the plane of x1 and x2, right? In this particular time, it happened to be like steadily increasing going up, but you could imagine one like steadily increasing going diagonally and so on. But at the end of the day, it has to be a linear function because that's what logistic regression assumes. And if we go back to our data, looking at this data, there's no linear function that will actually get us a good split, right? That'll actually split the data into all the ones on one side and all the zeros on the other. And you can kind of convince yourself of this by trying to like draw lines, right? If you draw a line like this, nope, no good. If you draw a line like this, nope, no good, right? So no line you draw can do much better than half-half. So for this particular data set, logistic regression is not such a good fit. Now note that this is a toy data set. I just kind of like came up with this. In a real world data set, you're probably not going to look exactly like this, but many real world data sets do have nonlinear patterns that come up and affect your data. So we can take some conclusions away from this, but don't sort of say, oh, because of this, logistic regression is useless. There's many cases where it can be quite useful. And in fact, it turns, we can also think about imagining a version of logistic regression where we add x1 times x2 as a feature. And that would actually be able to classify this. But again, then we have to know that, oh, I got to add this feature. Okay, so let's compare that to how k-nearest neighbors classifier does. So here again, I'm using scikit-learn's KNN classifier, and the code looks very similar, right? The only thing that's different here is the classifier. I'm using one with k equals 3. And again, I have the same fit, get the probabilities on the test set, then threshold them and draw the results. And if I draw these, you can see that the probabilities look very good, right? Way over here, they're like pretty close to 1. Way over here, they're pretty close to 1. And on the boundary, they're like kind of somewhere in the middle. And if we look at the predictions, we can see that they're mostly pretty good. They're not perfect. Like over here, it looks like we're predicting more zeros, whereas we know that like everything left of this line should be 1. But on the whole, it's pretty good. And if we look at the accuracy, it's 95%. So this is pretty good. And we can see that the KNN classifier does a really good job on this data set. So now let's take a minute to step back and think about what the pros and cons of these two different models are. So let's take a look at the pros and cons of these two different models. So let's start with logistic regression, right? We saw one pro is that it's really simple, right? There's only two, in the case we did, there's like 2 x's, and so there's only 2 parameters, right? It's simple. There's only k parameters, and in this case, k was 2, right? And it's kind of nice because it's simple and it's easy to say, I can tell somebody, if I get a prediction from my logistic regression model, I can go and tell somebody, hey, the model predicted this. And if they ask me, well, what if x2 was just like a little bigger? Then I could say, well, then if x2 was a little bigger, then the log odds would increase by beta times that little amount, right? So if I multiply beta 2 by that little increase, then I'm going to see a corresponding increase in the log odds, right? So I have a very intuitive interpretation of, well, which feature affects the output more, beta 1 or x1 or x2? Well, then I can just compare the coefficients. I can say, well, if beta 2 is bigger than beta 1, then that means x2 has a bigger impact on the output. If beta 2 is negative, then I can say, well, that means that beta 2 then, as x2 decreases, then the probability goes up, right? So there's a very easy interpretable sort of result coming out of the model, right? It's simple, it's interpretable. So, I described, you can just sort of you can read off how the output changes just by looking at the coefficients. It's simple, it's interpretable, Another benefit is with logistic regression specifically is that the loss function is convex, right? So if you remember this from data 102, the loss function is convex, which means, like it looks sort of like this, right? That at the end of the day, there's one correct answer and we're guaranteed to get to it. There's one answer and we're guaranteed to get to it. So that's really nice as opposed to k-nearest neighbor where it's like, well, like, if I have a different training set, maybe I'll get like a totally different answer. Or, it's like, well, the answer is just like whatever the training set says. And also storing or saving the model is really cheap, right? If I say, okay, I want to, fit a logistic regression to this data, and then I want to like save it to my disk and then load it up later. All I really have to save are these coefficients, right? Because to make predictions in the future, all I have to do is take those coefficients, multiply them by the x's, and run a sigma, right? So it's really easy to like save and reuse the model, right? It's small and easy to save. And this kind of goes hand in hand with it's simple, right? Like there's only k parameters, so that also means that it's like easy to save because you don't have to save k numbers. Okay, so those are the pros. What are the downsides of logistic regression? Well, we saw one big one, right? That that it makes this assumption of linear interaction, right? We assumed that the relationships between x1 and x2 and whatever the features are have to be linear. Now, you can get around this by doing feature engineering, right? We can say, well, okay, like let's put one column with x1, one column with x2, and one column that's like x1 times x2. And then logistic regression would actually just fit that little toy data set we saw just fine, right? So in this case, we can say we require feature engineering to model complex or nonlinear interactions. Right, so anything complex and nonlinear, we have to do some feature engineering. And again, this is like kind of a con, but maybe kind of a pro because maybe sometimes you know exactly what the features are, right? Or you're working with the domain expert. So this is only kind of a con, so to speak. But like at the end of the day, the base model is its simplicity can also be a con in that at the end of the day, you're assuming that there's some linear function and there's a signal, right? Like that's it. You're making that assumption and it's simple. And again, that's kind of a pro and also kind of a con. So you notice like there's kind of a blurred line between the pros and the cons. It's because the things that make logistic regression great are also the things that sometimes make it hard to use, right? It's sometimes like, if you have a partner, then the things that annoy you about your partner are also the things that make them great and wonderful. It's kind of the same thing with logistic regression. So what about k-nearest neighbors? So k-nearest neighbors has the biggest pro is that it makes no assumptions whatsoever, right? It's sort of this non-parametric method that makes absolutely no assumptions. So I don't have to like assume anything is linear. I don't have to do any assumption at all. It just works, right? As long as I have decent training data, it's fine. And the other thing about it is it's simple in one way in that it's very simple to explain how it works, right? I can go, I mean, in data 8, we teach k-nearest neighbor in essentially 1 hour of lecture. Obviously, that's not all the details. You have to get a deep understanding, but like the big picture is very simple to explain what's going on with k-nearest neighbor classification. So it's simple in that way. And here I'm putting simple in quotes because this is a different kind of simple than logistic regression, right? Logistic regression, the simplicity is in how few parameters there are, right? Whereas with k-nearest neighbor, there's like, it doesn't really make sense to talk about parameters, or if there are parameters, it's like every training data point is a like parameter because you're kind of like matching to every single one. So, there's like, we have to save, must save all training points. So this is, this is fine in this example where we have 100 training points and they're like 2 dimensions each. If you have like a large data set where you have 1,000,000 points and they have 1,000 features each, then you're talking about like 1 billion numbers that you have to save just in your training data. Note that there are like ways around this. Like there are variants like approximate nearest neighbors and so on that kind of like get around this problem. So this is not like hard and fast. You can't use any nearest neighbor thing. But generally it's sort of a limitation that you have to address when using these kinds of models. That's the first one. Another con is that it's really hard to interpret the predictions, right? If you remember that like graph we were looking at, it's really hard to say, well, like what if, what in general, like what happens when I increase, x2 by 4? It's like, well, it depends. Like if does that move you closer to one of the training points, then it'll change. And if it doesn't move you closer, then it won't, right? So you can kind of like look at the graph and look at the decision boundary like we did on the picture to sort of get some sense of being able to interpret what's going on. But it's not nearly as easy to interpret and really like, dig into the internals of the model and figure out, aha, this is what this means, right? This means that, this feature is more important than this feature because this is positive, this is negative, this is bigger than that one. So it's a lot harder to interpret. Right? If I want to say like, well, there's a particular point, why did you predict 1 for this? You can say, well, it's because it was close to those 5 training points and those 5 training points all had 1, right? Like, let's say I'm trying to, predict whether, I don't know, there's some disease present in an image. And I say, okay, like here's a new image. Why did you predict that this has heart disease, right? And you can imagine in a medical setting, it's really important to be able to say why, because that is necessary for our understanding of like the science behind it and being able to explain to the patient and being able to explain, whether our predictions are correct and justify them. And if the only thing you can say is, well, it's like these 5 other, examples I saw, and 3 of those that were positive, so I'm just going to say positive. So it's not as compelling of an explanation. Yeah, so this is kind of the overview of logistic regression canon. There's plenty more pros and cons. This is not an exhaustive list by any means. I'm definitely oversimplifying a little here, but I want you to take away like a big picture here is that, logistic regression makes assumptions about the structure of the problem. And in return for those assumptions, we get something back, right? We get a model that's very easy to interpret. We get a model that tells a clear story, right? It tells a clear story that if I know the X's and I know the betas, then this is how the Y happens, right? But in return, we have to like make some assumptions. And to model anything more complex, we need to do some feature engineering. And you can imagine if you add another feature for like X1 times X2, then how do you interpret that one? It's like, well, if the product of these 2 features increases by this amount, then that. So like you lose a little bit of the interpretability once you add more complex features. Unless those features are themselves relatively intuitive. So, there's these trade-offs that we get with a parametric model. Whereas with a non-parametric model, we get a different set of trade-offs, right? The model like just sort of works, right? You can just like take a k-nearest neighbor classifier, throw it at a problem, and as long as it's not like too high dimensional and you choose k, right, and so on, then you're going to get, hopefully decent-ish performance, right? But there's a price you pay for that, and you don't have to make any assumptions at all. But there's a price you have to pay for that. Your model is a little harder to explain, a little harder to interpret. And so these trade-offs it's not a hard and fast, if you get one, you can't get the other. But generally, there's like this sort of universe of, there's like, how well does the model do? How easy is it to interpret? What is its accuracy? What is its assumptions? All of these different factors come into play. And it's usually not just which model has the best accuracy, right? You really have to consider all of these different facts when you're looking at data. And so this is why, in this class, we spent so long on these kind of like parametric, like model culture, or algorithmic, or sorry, data modeling culture, as Leo Breiman calls them, approaches, because they're very powerful and we want to explore what are the assumptions being made and what do we get for those assumptions? Whereas with the non-parametric world, it's like, well, we don't make assumptions. And so in these two lectures, we're going to cover, well, what do we lose when making that? And what do we gain in making that? In this video, we're going to talk about decision trees. Decision trees are a prediction algorithm, classification and regression that are non-parametric. They don't make any assumptions about the input data, but they're also very simple and also easy to interpret. And a decision tree is kind of what you'd get if you just said, like, make a set of rules, right? Like, if this variable looks like this, then do that. If this looks like this, then do that. And we'll make that a little more concrete. And decision trees are also a really powerful building block that are used in algorithms like random forests, gradient boosted regression trees, all kinds of other kind of more complex algorithms that are really popular and widely used that use trees as a building block. So let's start there, and then next we'll talk about random forests. Okay, so how do we actually build a decision tree? Well, let's go back to this data set that we've been looking at with the sort of like checkerboard pattern. And let's try to construct a decision tree to help us do classification on this data. And so we're going to have, the first phase is we're going to actually build out the tree, and we're going to use the training data to like build it out. And then we're going to see how we can use that tree to classify new points. So the way this tree is going to work when we classify new points is we have some value x1, x2, right? Because in this case, it's two features that comes in the top. And basically, at each node, we're going to make a decision. Is some value greater than, less than, and we're going to go down one branch of the tree. And then we're going to go, have more branches there. We're going to go to that branch, then go down that branch. And at the end, we're going to end up at the leaves. And in each leaf is going to have a decision that tells us what to do if we reach there. Okay, so what does that actually mean? And what are our decisions? What are these decisions anyway? Well, each decision is just going to be like a split of the data. We're going to say split the data in half, either using x1 or using x2. In general, if you have more than two features, you can split on any one of the features. But in this case, there's only two, right? So we're drawing a horizontal line or a vertical line. So to start with, and so how are we going to draw the lines? We're going to draw them so that each sort of sub part is as homogeneous as possible, right? As in all the points look the same in terms of their y values, right? So we want splits that give us like blocks that have all the same y value in them. All right, so now where do we start? Well, I'm going to start with x1 kind of arbitrarily because, in this case, they're symmetric. And, any split of x1 I do is going to give me a 50-50 split on the y's. So not that great. But in this problem, I know that there's something special about x1 being 0, right? And so that means my first split is going to be x1 being 0. And what does that mean? That means that I now have two branches of the tree. There's one for x1 less than 0 and one for x1 greater than 0. Now, for x1 less than 0, what do I do then? Well, then I'm on the left side of this plot. And there, splitting in terms of x1 again isn't really going to help me. But if I split in terms of x2, then I'm going to be able to get really, really homogeneous subgroups. And that split is going to be at x2 equals 0. Right? So if I do the split at x2 equals 0, then everything above is all purple. They're all y equals 0. Everything below is all yellow. It's all y equals 1. So that means that the next thing over here is x2 split at 0. And if x2 is less than 0, then we're in the bottom left part of this, and then we're done, right? So we say, okay, then if you land there, your prediction is y equals 1. Sorry, not 0. Your prediction is y equals 1. It's the yellow gold prediction. Now, what if you go down the other path, x2 greater than 0, you're above this line, then in that case, everything's purple, so my prediction should be y equals 0. Now, similarly, on the other branch of the tree, so now we're looking at the right half of the graph, it turns out, well, the split is the same. In this case, it's the same in general. You can split, you can have a different value for your split. You can even choose a different variable for your split. The possibilities are endless, right? You're really just choosing the split that gives you the most homogeneous subgroups so that once you get down to one of these leaves, you can say, aha, in the training data, all the points that ended up in this leaf, or almost all the points, had y equals 1. So I'm pretty sure that the answer is y equals 1. So now here, this side is also x2, 0. And the left branch is x2 less than 0. The right branch is x2 greater than 0. And just like before, the split looks like this, right? And so if we're in x2 less than 0, then we predict y equals 0. And over here, we predict y equals 1. Great. And so now we've built up our tree, right? Every leaf is defined. All the, this is a full tree. And this is a particularly nice example because this data set is like really simple. And so all of the leaves are perfectly homogeneous, right? And the tree is also very symmetric. In general, you may end up with like trees that are like a little imbalanced, like, one side might be a little deeper. This tree also is not that deep. In general, trees could go a little deeper. So what you get kind of depends on your problem and like how deep should the tree go? What does it mean for like how do you choose the best split? These are all questions that are part of the algorithm of how you build trees. The details are kind of beyond the scope of what we'll talk about in this class. You can read up. The most popular is an algorithm called CART, Classification and Regression Trees. But this is the high level idea behind what's going on. Okay, so that's decision trees. They're pretty, very simple algorithm, very explainable, right? You can show this tree to somebody and they can say, well, like, I had this point at 3, -7. What if it had been at 3, -6 instead? You could go and look and say, well, actually, I see on this tree that, I see from this tree that all of the, the x2, the only splits are at 0. So -7, -6 doesn't matter, right? The only difference is if you ended up, crossing over the threshold. So these are also very easy to explain. You can show this to somebody, even a non-expert, and they can pretty easily understand like the set of rules that you've defined in this tree for what's going on. So in that sense, decision trees are very nice. They're a non-parametric method. We didn't have to assume anything about the distribution of the points, anything about the x's, anything about the y, anything about the relation between them. We just came up with a set of rules that we encoded in this tree. And in return, this tree is pretty easy to interpret. The only downside is in practice, these trees can, not work not that well when you have more complex data or noisier data. And we'll see an example that highlights that and use that example to build random forests. In this video, we're going to talk about random forests and other so-called ensemble methods. So we've talked about decision trees, which are like a pretty nice, simple, elegant model, doesn't assume anything about the distribution, gives you a prediction, you build out this tree. And now let's say, well, what if I wanted to use not just one tree is good, many trees could be even better. So random forests are an idea that say, let's not just take a single tree, let's take a whole bunch of trees, where each decision tree is trained on a bootstrap resampling of the data. And this is a really powerful idea because now you don't have, the trees are not all just identical, it's each one is a little different, right? And it's this idea where like we're taking a bunch of different models and each one is trained on a bootstrap resampling. This is called bootstrap aggregation or bagging. And it's really powerful because each model can kind of like capture a different aspect of the data. And each one is kind of like jittered a little, right? And you can imagine, that means that they're less likely to overfit your data because each one is kind of like fitting something random. And then at the end, if you average them all together, well, the kind of like jittering kind of averages out and you get something that looks very nice. The other big idea, so the first big idea is bootstrap aggregation, where each one is trained on a bootstrap resample. The second big idea is random feature selection. So you can imagine, we've been looking at these toy problems with like 2 features, but in a lot of real world problems, you have a lot of features. Your problem may be very high dimensional and, maybe looking at hundreds, thousands of features. And it seems like training a decision tree on 1,000 different features, then like you have 1,000 different choices of how to split your data at every step, right? And so that means that your tree is going to get extremely deep because you have to split among each of your 1,000 features, right? If you have 1,000 features, even if you just do one split in each dimension, that's like a depth of 1,000, right? That's like a super deep tree. And so what a random forest does is it says each of the trees is only going to get some random subset of the features. And so we're randomizing both the like data points that it's getting, and we're randomizing the features that it's getting. And the features, there are fewer of them. So each one gets like fewer features, random resampling of the data, and then we train each one separately, and then they make a prediction on the overall data set. So this is a very powerful idea, a very simple idea, and also a very powerful idea. So this is one way of doing ensemble methods. Another way is doing something called boosting. So with boosting, it says, well, instead of just like doing all these things randomly, why not train one, look at where that one does badly, and then just kind of like train another one only on the ones where it does badly, and then look at where like those two do badly, and then train another one just on the one where those do badly. So we're not going to talk much about boosting in this class, but it's another way of doing ensembling, right? So two big ideas with random forest. One is bootstrap aggregation, also known as bagging, because you're B for bootstrap, ag, bagging. And the other is random feature selection. And in the notes, there's a little demo on implementing a random forest classifier and kind of like seeing where that goes. I encourage you to check that out. All right, in this video, we're going to talk about neural nets. And in this class, we're going to focus not so much on the nitty gritty of like, here's the latest technique from last year that, gives you like the best performance when you train a neural net. Instead, we're going to focus more on the big ideas. And specifically, we're going to focus on big ideas like backpropagation and automatic differentiation, which at the heart of it are just ways of computing derivatives in clever ways that make it really easy to like build these large models and then just automatically figure out what's the derivative, right? You've all had the experience of like, here's a problem. How do you find the best value? Take the derivative, set it equal to 0. Or in gradient descent, it's like, well, take the gradient, which is multidimensional derivative, and like move in that direction. And so backpropagation is just like a clever way of, well, you write the code and the program will automatically figure out what the derivative or gradient is. And automatically, we'll actually go under the hood and figure out how that works. Okay, but to do that, we'll first start by thinking about how a neural net works. So to think about a neural net, let's start with linear regression. So we have y equals wx plus b, right? X here is a vector of features, or you can think of it in an entire matrix of features for a bunch of data points. Y is a vector of your outputs that you're trying to predict. And you have y equals wx plus some constant. Now, this is great, but we've said that in order for this to work well, you need to have good choices of features for x, right? You need to, choose good features. Maybe, you need one feature that like depends on some of the others. There's a lot of feature engineering that can go into this. And so neural nets, one way of looking at it is, well, what if I could use like a linear regression or linear regression-like thing to actually figure out good features for me? So instead of just y equals wx plus b, what if I said y equals w1x plus b1, where here w1 is now an entire, instead of a vector, it's a matrix, right? So you can think of like w1 is like w11, w1 m, all the way to wnm, right? Where each row of w corresponds to like, what we do in standard regression. And so that's going to generate one feature, right? So one row is going to get multiplied by the x's, and that's going to give me my first feature. And then the second row is going to get multiplied by the x's, and that's going to give me my second feature. And then the next row and so on, right? So this is like, I'm going to use this to generate my features. And then I'm going to have a second round of linear regression on that, right? Seems like not a bad idea, right? Like, let's just use linear regression to generate the features for me. And so W1 is a matrix that like mixes all the x's together and gives me some set of like features that are like combinations of the x's. Maybe there's something interesting going on there. And then W2 actually does the linear regression. And you can imagine like you can stack more and more of these. Except there's a problem here. There's a really big problem, and this doesn't actually, what I just wrote out doesn't actually get us anything over the first equation I wrote. So I want you to take a second and look at it and think about why. Did you see it? It turns out that here, because everything is linear, that this just reduces to a standard linear regression. So what do I mean by that? Well, if I actually do it this way, right, then this is just y equals w2 w1 x plus w1 w2 b1 plus b2, right? And what is this? Well, this is really just like a matrix times x plus like a constant, right? So this is really the same as this, right? Because everything is linear, then we can just like linear multiply everything out and it ends up being just the same. So darn, this idea didn't quite work. But we can make one small tweak and everything will actually work out great. And what we're going to do is we're going to take this, copy it, and I'm just going to move it down here. And all I'm going to do is I'm going to say, oh, we just start over. So we'll just say, instead of that, we'll say y equals w2 times some nonlinear function of w1x plus b plus b1 plus b2, right? All I'm doing is adding in this extra nonlinear function. And boom, as soon as, as long as I guarantee that f is nonlinear, then this doesn't simplify. And why is it nice that it doesn't simplify? It means I can express more complex things by chaining these together, right? Like if I do it the earlier way, right, where I just said y equals w2 times w1x plus b1 plus b2, then I could like chain w3, w4, and at the end it would still just boil down to like one regression. Now here, each of these w's is going to be doing something interesting and different just because I added that simple nonlinear function. So that's it. That's like the big idea behind neural nets is like, well, one of the big ideas behind neural nets is just like add a nonlinear function in there and boom. Now, what does f look like? In like the original neural net papers, f was a sigmoid. But nowadays, people tend to use a function called the restricted linear unit, or ReLU, which is just a really fancy way of saying a function that looks like this. It's like for x negative, right? So this is your axes, and your function looks like this. If x is negative, then y is 0. If x is positive, y equals x. Very, very simple function. Okay, so now this is it. This is a simple 2-layer neural network. So great. Now, I plug in x, I want y. Now, the thing is, how do we figure out what the values of w1 and w2 should be? Well, that's where we need to start taking derivatives, right? I need to take the derivative of I need to take I need to have some kind of like way of computing a loss, and I need to take the derivative of that loss with respect to the values. And so we'll get into that in the next video. How do we actually figure out the best values of w1 and w2? All right, so now we have this model, right? This small 2-layer neural net. And it tells us, okay, given x, you have, and if you know w's and b's, then here's how you get a prediction for y. But how do we actually figure out what the w's and b's are? Well, in linear regression, we could use the least squares solution, right? Which it turns out was like the optimal value if your cost function is the squared loss. Now, we're going to do something similar here where we're going to set up a loss function that's relevant for our problem, and we're going to optimize it. But since we won't be able to do something as easily as we did with linear regression, we're going to use stochastic gradient descent to optimize that loss function. And as a reminder, stochastic gradient descent is this really powerful sort of workhorse algorithm that lets you find the optimal values of any function, sometimes local optima, but still optimal values, as long as you can compute derivatives, as long as you can compute the gradient. So we define a loss, right? The loss says, okay, given a particular set of values, w's and b's, and the actual value I got, actual data I got y, how good were those w's and b's? And we have two versions of the loss function. One is the squared loss, where we take the prediction minus y squared. The other is the binary cross entropy loss, where we plug in the same prediction, compare that to y using cross entropy. So these are both reasonable loss functions, one good for continuous, one good for binary. You can use other loss functions, but at the end of the day, we defined some loss, and now we need to minimize it. We want to make this loss as small as possible, right? In the case of optimizing the squared loss, you can see it's small when the thing I've highlighted in y are as close together as possible. So how do we optimize it? That's where SGD comes in. SGD stands for stochastic gradient descent. So how does it work? It works by computing the gradient. So what is the gradient? It's a vector of partial derivatives. And these look like partial L with respect to W1, partial L with respect to W2, partial L with respect to B1, partial L with respect to B2. So I got a little sloppy there. But this is essentially a vector of partial derivatives, one for each parameter in your model. And even this is kind of a simplification because there's not just a single W1, W1's a matrix. So you actually have a really big vector, one for each item in the matrix. But this will, kind of serve our purposes for now. Okay, so this is the gradient vector. And what SGD says is, okay, what gradient descent says is you start with some initial values for your parameter. You pick them, either randomly or maybe you have some intelligent guess. Whatever you want, you start with some values of theta at step 0. And then what we do is we say, okay, the next value of theta, theta 1, is the previous value, theta t, minus the gradient. And you take the gradient and you evaluate it at the current, because remember, the gradient is a function, right? Each of these derivatives are functions, right? The derivative of a function is another function. And so this is all a bunch of functions, and we take a step in the direction of that. And how big a step we take, well, that's controlled by this parameter alpha called the learning rate, right? So this alpha is the learning rate, right? So big values of alpha means we're taking big steps towards the gradient. Small values mean we're taking tiny little steps. In practice, you want to find some good in between. There's kind of an art and a bit of a science to doing that. Then there's y, which is the observed data. Then there's the current value here, and this is the gradient. Okay, so this is gradient descent, where you just run this a whole bunch of times until your thetas converge, right? Until theta t plus 1 looks the same as theta t, looks the same as theta t minus, it's not changing anymore. So this is just plain old gradient descent. Then there's stochastic gradient descent. I've solved a bunch of problems using gradient descent. 95+% of the time, you don't actually want to do this with all of your data. You don't want to try to compute this gradient using every single data point. You usually do it in batches. So you'll take your data and chunk it up into little batches. How big the batches are, again, there's a bit of an art to that, but you choose batches of a certain size and you do it only on that. So the S in the stochastic basically says you work in batches. Just like how recipes say to work in batches when you're making soup, right? It's the same idea here. You just chunk up your data and do a little bit at a time. You know how if you're making soup, not all of it's going to fit in your blender. So you put in a little bit, make that, then do the next. Same thing here, especially if you have a large data set that doesn't all fit into memory. You can do a little bit of it at a time, compute the gradient, and then go from there and do the next little bit and the next little bit, and then repeat over and over and over. Okay, so that's stochastic gradient descent. So we can see that how do we actually use this? Well, we need to be able to compute this vector of partial derivatives, right? So SGD is great as long as we can compute the gradient. So how do we actually compute the gradient? Well, I'm looking at this function, right? If I go back up here and I'm looking at this and I see that I can actually write out the computation for how to compute the gradient with respect to, W1, with respect to B1. but it feels like there's going to be a lot of redundant work, right? And if there's like many, many layers, then it feels like we're like differentiating all the way like into the, parens after parens after parens. And it feels like there's a lot of redundant work. And so next we're going to talk about backpropagation, which is a way of computing derivatives or gradients very, very efficiently. All right, so how do we actually compute gradients? So instead of dealing with this like complicated, like squared loss with the loss function, let's start with a really simple gradient, and we'll compute the loss there. And then we'll kind of like learn how we can do backpropagation to make it more efficient. Okay, so let's say I have a simple loss function that takes in three values, a, b, and c, and it's just a plus 3b times c squared. Really simple function. I just kind of made this up. Doesn't really look like any actual loss function anyone would use, but it's going to help us learn like how we compute gradients and how we make it more efficient using backprop. Okay, so in order to compute the gradient of L with respect to these three things, I need three partial derivatives, right? I need the partial with respect to A, I need the partial with respect to B, and I need the partial with respect to C. And to actually compute this, I'm going to use the chain rule, right? Like, because this is a compound function, so I'm going to be using the chain rule. And to make like it really clear what I'm doing with the chain rule, I'm going to define Q to be equal to A plus 3B, and I'm going to define R to be equal to C, just to like make things really clear when and where I'm using the chain rule. Okay, so partial with respect to A, well, the A depends on Q, right? This first term. So this is really partial L with respect to Q times partial Q with respect to A, right? So this is partial derivative of L with respect to Q. Well, L is Q times C squared, so this is just C squared. And then partial of Q with respect to A is just 1. Same kind of thing for B. Again, I need to know partial L with respect to Q, and then Q with respect to B. So what is partial L with respect to Q? Well, it's like Q times C squared, so it's C squared. Huh, I just had to do that twice. Kind of annoying, but oh well, not the end of the world. Now, next I have to do partial Q with respect to B. That's just 3, right? Part derivative of A plus 3B with respect to B is 3. With respect to C, well, this is now partial L with respect to R, because C only depends on R, times partial R with respect to C, which is the derivative of L with respect to R is A plus 3B, and then the derivative of R with respect to C is 2C. Okay, great. So this here is our vector of, so this is our gradient vector. Great. So we computed the gradient. It kind of took us a little bit of time. This is like even the simple example kind of like took a bit of working out. And notice that we had this redundant computation, right? We had this redundant thing where we had to do this, this term showed up twice, right? And why did it show up twice? It showed up twice because inside of Q, there's 2 different variables. So any case where you have like multiple variables like buried inside of a compound function deep somewhere in your expression, then you're going to have to do repeated computation. And this is fine for a simple example like this, but when you're trying to compute the derivatives, the gradients for a neural net that has thousands, millions of parameters, then that kind of redundancy makes it really, really inefficient. And so backpropagation is a way of computing this gradient very, very efficiently. And so now we'll kind of see how we do that. Okay, so now let's talk about how we can actually compute this gradient very efficiently using backpropagation. So what is backpropagation? It's just an algorithm for computing gradients efficiently. So in order to do that, we need to kind of transform this computation from the algebraic expression we have here into a slightly different representation of the same thing. And so I'm going to write out A, B, and C, and I'm going to like draw out the computational flow of what the process looks like. So first we take B, we multiply it by 3, we add that result to A, then we take C, we square it, and we multiply that result by a plus 3b. And that gives us the loss, right? This is just a different way of representing the exact same process. Now, what backpropagation is going to do is it's going to say, okay, let's have a really efficient way of computing both the loss and the gradients with respect to A, B, and C, assuming we know that they take on specific numerical values. So if we look at the computation we did last time, we can see that we, for example, for the partial with respect to A, we kind of started off at the end, right? We sort of like, what's the partial with respect to Q, right? Q is like the result of A plus 3B. And then we kind of like went backwards. Okay, now then what's the derivative of Q with respect to A? And so let's try to follow a similar process here where we'll compute the loss. And then to compute the gradients, we'll start at the end and kind of like work our way backwards. So what exactly does that look like? Well, first we got to compute the loss. So like I said, we need backprop works with specific values. So I'm going to say A is 2, B is 3, C is 4, just kind of arbitrary. And I'm going to write the values to like compute the loss on top of each of the arrows. So A is 2, B is 3, C is 4, 3 times B is 9, 4 squared is 16, 2 plus 9 is 11, 11 times 16 is 160, 176, right? Great, so now I've computed the loss. The loss is 176. Now, how do I go about computing the gradient? Well, we've already said we kind of like want to work backwards, right? So how exactly do we do that? Well, we'll start by just, also one other thing. This thing we called Q, and this thing we called R, right? And so we'll start by computing the gradient of the loss with respect to itself. So this may sound silly, but it kind of like gives us a starting point for the whole algorithm. What is the partial derivative of the loss with respect to itself? It's just 1, right? Derivative of any variable with respect to itself is 1. And intuitively, right, like if you change the loss by a certain amount, the loss changes by that same amount. So this is easy. Now, what is the derivative of the loss with respect to Q, right? In other words, what is the gradient on this branch of the tree? Well, what are we doing to Q to get the loss? We're taking Q and multiplying it by 16, right? We take Q as 11, we like multiply it by 16 to get the loss. And so in order to get the gradient, what's the derivative of something that you multiply by 16 to get something else? It's just 16, right? Like when we multiply by something, the derivative is the thing we multiply by. So here, I'm going to write the gradients on the bottom. This is 16, right? And so we kind of like took the number from down below because that was what we multiplied to get 176, and that's the gradient. We can do the same kind of thing for the bottom branch over here. So here, how do we get R? How do we go from R to the loss? We took R, which was 16, and multiplied it by 11 to get the loss. So to compute the derivative, we just say, well, we multiplied by 11, so the derivative is 11. And it's sort of like because of chain rule, we need to keep multiplying as we work our way back, right? So this is really like 11, but it was like 1 times 11. It was 1 times 16. Okay, so now let's keep going. So how about next, we'll do something a little on the easier side. We'll start with A. So how do we compute the derivative of A, right? With respect to, of Q with respect to A, right? Like we're kind of working our way back. And so right now we're here, we have, the gradient of, the partial with respect to Q is 16. So now how do we go from that to get the derivative of the loss with respect to A? Well, what do we do to A to get Q? Well, we just add 3B, right? What's the derivative of something that you add a constant to, right? Like we added 9, right? 3B was 9. So we took this thing and we added 9 to it to get Q. What's the derivative of something that you add 9 to? It's a constant, right? So this is, the gradient is 1. And so we just take 16 times 1. And over here, we get that our value is 16. Great. Now, what about the gradient of this like kind of branch that we don't actually have a name for over here? Well, same thing, right? Like we're taking that and we're adding 2 to it, right? We're adding A, which is 2. And so 16 also just stays as 16 here. So now is where things get interesting, right? Now let's compute the gradient with the derivative with respect to b. So what is the derivative with respect to b? Well, in order to get from b to this thing here, right? This sort of like the thing on the right, in order to get from b to that, we multiplied by 3. So what's the derivative going backwards? When you multiply something by 3, the derivative is just 3, right? So now we take 16 and we multiply by 3. Why are we multiplying? Chain rule. So this becomes 48. Great. And now we already have 2 of the components of our gradient, 2 of our partial derivatives, right? The partial with respect to a is 16, partial with respect to b is 48. Great. Now let's go on the lower branch of the tree. So finally, let's figure out the partial with respect to c. Well, so far we have 11, and we know, like, we've been doing this, we need to like multiply by something. How did we get from c to r? Well, we squared, right? What's the derivative of something when you square it? It's 2 times the thing at the input, right? Like derivative of x squared is 2 times x. So if I have, y equals x squared, the derivative of y with respect to x is 2x, right? So then here, my derivative is going to be 2 times the thing at the input. So thing at the input was 4. So my derivative is 8. And again, because we're using the chain rule, we need to keep multiplying all the way back. So this becomes 8 times 11, which is 88. All right, so now we have our 3 derivatives. And we can actually see if we go and check. I wrote out the math for each of these. Right? C squared was the partial of L with respect to A was c squared times 1. C squared is 16, right? And we can kind of see that 16 showed up over here, right? The 16 kept showing up over here because it's the partial of Q, right? And Q is here. And so we can kind of see how the chain rule computation translates over to the graph, right? So we're kind of like doing the same thing 2 different ways. Okay, and that's all there is to backpropagation. You do a forward pass to compute the loss, and then you kind of like go backwards to compute all the gradients. And you kind of you're required to have specific values. In this case, we knew A is 2, B is 3, C is 4. And in practice, whenever you're doing gradient descent, you always have values, right? I know that, like I have my theta sub t, or theta superscript t, which is like the parameters this time. And so I plug those in, compute the loss, take the derivative, and boom, I'm done. Okay, so this was an example of doing backpropagation. And how did it work? Well, the way it worked is we like built up this computational graph, and we kind of like, did a bunch of stuff. And so let's kind of like break down how this works, right? So we had, so like, what do we actually need to be able to do this in practice, right? To do any operation, right? Any operation that has like, 1 or more inputs and produces an output. So we need to be able to like actually run the operation, right? If it's multiply, we need to like multiply the inputs. So when we do the forward pass, right? Like when we're computing the loss, the forward pass, we just run the operation. And on the backward pass, well, how did we do things on the backward pass? We just simply multiplied by the derivative of the operation, right? So each branch multiplies the derivatives by the derivative of the output, partial derivative of the output, with respect to that branch, right? And that's sort of like, if the operation is squared, then we multiply by 2 times the input. If the operation is e to the x, then we multiply by e to the input, because derivative of e to the x is e to the x, so on. So we just have to define for every operation. We not only have to know how to do it, we have to know how to compute derivatives. And in any program where you're doing math, it's easy to like say, what's the derivative of e to the x? Straightforward, is e to the x, right? What's the derivative of this big complicated expression? Well, you don't have to worry about that because you just have these little individual building blocks. And as long as you can compute the derivative of each one, then you can compute the derivative of the whole thing. Okay, that's all there is to backpropagation. So now that we've gone through backprop in a really simple kind of toy example with like a plus b, 3b times c squared, what does it look like in an actual model? Well, so remember our two-layer neural net that we made, right? The prediction y hat is equal to W2 times, some nonlinear function. Here I'm just like using the sigmoid function of W1x plus B1 plus B2. And then the loss is y hat minus y squared, right? We're using the mean squared error loss or squared error loss. And, if you want, we could use the root mean square error loss, that would just add an extra square root here. And this is the computational graph for that, right? We have x, w1, b1, w2, b2, and y. And we see that, we first multiply x and w1. This times here is really like a matrix multiply. Then there's like a plus. This is like a vector add. Then we use the sigmoid function, multiply again by w2, add b2. And then this is y hat, right? This is our prediction. We subtract off y and we square, and that gives us the loss, right? And so, we're drawing out this so that we can kind of understand what's going on. But in reality, in, like modern programming frameworks, as you write out your code that does this, it constructs the graph for you automatically behind the scenes. And we'll see a demo of how that works. And so now, how do we actually compute the loss? Well, how do you do gradient descent, right? We initialize, values, we compute the loss, right? We plug in the x that we know, the y that we know, our initial values for the parameters. And, we just run the forward paths on the graph, right? Which is essentially do the math. And then we get a loss. And then we can use backpropagation to say, okay, say our loss was some number, like, I don't know, like 1,322 or something, right? Then over here, it's like, okay, well, how do we compute the gradient? Well, gradient here starts at 1. Then gradient here starts at like whatever 1 is times, this is like 2 times the input, right? 2 times whatever was here. And then for subtraction, like whichever one was negated gets multiplied by -1. The other one does not. And then, and so on and so on and so on. And we work our way back, right? So this is like how it would work in a real problem. We'd like to go through the plus, the multiply. We already did the plus. It just passes through. The multiply, we just kind of like multiply by the whatever's on the other branch. The sigmoid, we can take the derivative of the sigmoid. I could just like write it out. Or you could even like break it down into like, it's 1 divided by 1 plus e to the minus thing. And you could like expand that out. And then you could easily write down the derivatives for each component. In practice, people tend to just, like do these building blocks and have the derivatives for each one, and so on and so on. So notice here that, like we could compute the gradient with respect to everything, but we don't actually need all of them, right? Like, for example, y, we don't need the gradient with respect to y. Y is fixed, right? Same thing with x. We don't need the gradient. We're not trying to optimize over x. We're only trying to find the best w's and b's. And so if we're only finding the best w's and b's, we don't need the gradient with respect to x. So that means that, like we get all the way here, and once we go here, we can save a little tiny bit of time by not computing this. And we only have to compute this. Same thing here. We can save a little bit of time by not computing the value on this branch and so on. And we'll kind of see again what that looks like in code in a bit. So this is what backprop in like a more kind of more realistic model would look like. In practice, you'd have like many layers and, it would kind of look similar. You just have more and more and more. And why are we doing this? Again, let's suppose we had like 5 layers like this, right? And I wanted to compute the derivative with respect to W1, right? The thing that happens first. Well, in that case, I'd have to like, do the chain rule W5, then like W4, W3, and like, do a lot of like chain rule multiplications. And then I'd have the partial derivative with respect to W1. Then for B1, I'd have to do a lot of the exact same computations all over again, right? I'd have to like W5, like, the partial and all the way down. And so it saves us a lot of work to only have to do any individual thing once, right? And so backpropagation is an example of a dynamic programming algorithm where instead of like doing, to do some computation, instead of like doing things over and over and over, we're kind of structuring it in a really efficient way so that we only have to do things once and we can reuse those as many times as possible. Right? Like this intermediate value, right, which is this intermediate value, which is the output of like the first layer, sigma W1x1 plus B1. right? We're using this over and over and over in here, right? But we only compute it over in here, right? But we only compute it once. So that's kind of where backpropagation is helpful. It's a dynamic programming algorithm that lets us compute gradients very efficiently. And, like we're looking at it in the context of neural nets, but really people use it everywhere. The examples we did in PyMC3 use an algorithm called Hamiltonian Monte Carlo, which requires actually computing the gradient of your function you're trying to sample from, your unnormalized function, so that you can kind of like, figure out like which direction to move in nicely. And in order to compute those gradients, it uses something exactly like this. PyMC3 is built on top of a library called Piano, which actually uses all this like automatic differentiation stuff under the hood. And in the next video, we'll see a demo using a library called PyTorch and kind of like get a flavor for how this works computationally. All right, so now let's look at how a demo of how backpropagation works implemented in code. And for this demo, we'll be using a library called PyTorch, pretty popular library that people use for neural nets. It's also, a very useful general purpose tool. Generally, people tend to use, libraries like PyTorch, TensorFlow, or JAX. There's these are like the big ones. There's also Piano. There's like several others as well. It's an active area of research and development too. Okay, so I have this code I've written. So I'm generating A, B, and C. A, B, and C are torch tensors, which are like PyTorch's equivalent of NumPy arrays. It's like you can think of it pretty much just like an array, except it has like this fancy like automatic differentiation, like backpropagation stuff under the hood. And in order to be able to use that, when we create variables like this, I need to write requires grad equals 2. True. This is saying that like I want to compute the gradient with respect to A at the end of the day with B, C. Remember, like we said, we don't need the gradient with respect to like X and Y, only with like W's and B's. Usually when you define variables like this, the default, it assumes that you're defining data, so it doesn't. But we're telling it, okay, I want the gradient. Okay, so that's A, B, and C. And I'm going to say Q equals A plus 3 times B, and R equals C squared. And I'm going to print Q, I'm going to print R. And now it says Q is a tensor, value is 11, which is what we got before, 2 plus 9. And here it says gradient function equals add backward, right? So it knows that Q knows that in order to compute its gradient going backwards from Q, that the function was add, right? And so it knows how to compute the gradient for add. Same thing for R, the value is 16, right? C is 4, C squared is 16. And the gradient function is pow backward, right? Because remember, C came as a result of raising C to a power. And so to compute the gradient, like there's whatever the derivative of a power expression is, right? Raising C to a power. Okay, so that's Q and R. And we can write L equals Q times R and print L. And we get 176. Great. Exactly what we expect to get. Now, how do we actually now this is how we compute L. And now how do we tell it, okay, the L is the end, that's the loss. Now I want to compute the gradient of everything, of L with respect to everything, right? A, B, and C. So if I do L dot backward, then boom, just like that, PyTorch does all of the backward computation, and I can see the gradients here. A dot grad is 16, which is what we got before. You're welcome to flip back to the video and refresh the memory. We can see like B dot grad is 48, C dot grad is 88, and we have all these gradients, right? And so this is how it works is, it stores every variable has associated with it, right? Like all the intermediate parts of the computation have associated these like little extra values, and to compute the gradient, we just kind of like, have the value, and we also have the gradient. And so the code takes care of remembering all of that and doing all that computational graph stuff for us. So this is a really powerful building block. It's useful for, optimizing neural nets and, fitting them. It's also useful in any problem where you're trying to use gradient descent. And, because gradient descent is such a powerful tool, this is a really powerful building block that people have used, not just for neural nets, for everything. So hopefully now you have a good sense of like what backpropagation is, why we use it, and how we might use it in neural nets.